and this is a talk about design for additive manufacturing. So to all of you in the room, thank you for making it out, and for everyone on the webcast, thank you for tuning in. So I'm going to hammer through this. I got a lot to cover, and hopefully we don't run out of time here. But this is relatively informal, so actually it's very informal. So if you have questions, just raise your hand, and I'll do my best to answer them as we go. So a little bit about me. Like I said, my name is Paul DeWise. Back in 2010, I started, or 2009, I started an engineering company out of my dorm room of all places. Essentially, kids were paying me to do their CATIA homework for them, so I thought maybe I could get companies to pay me to do their CATIA work for them. And so turns out CATIA is great, but SOLIDWORKS is way better if you're trying to build a business and you want a lot of customers because everyone uses it. So very quickly, I got into SOLIDWORKS, and for the last almost 10 years now, it's been very SOLIDWORKS centric. So from 2009 to 2016, myself and a small but growing team built up DE into a full-service engineering company. Do a lot of work in automotive, aerospace, a lot of automated equipment, agriculture, mining, just very diversified. And so throughout that, we would do some product development here and there, and I had a 3D printing vendor that I used in the next town over. One of the early 3D printing vendors, a company called Select Manufacturing, they got started in 1994. Became friends with the guy who owned it, and eventually he was ready to retire, and he didn't really have a plan as to what to do with it. So we were friendly, and he said, hey, do you want to buy this business from me? And not knowing anything, never having bought a business, I'm like, sure, let's do it. And so in 2016, I acquired the assets of Select, and we moved them into our facility and formed Forerunner 3D Printing. And so since 2016, I've been kind of double duty as an engineering sales guy and a 3D printing sales guy. And that's why this presentation was pretty easy for me to put together, because I live in this world of design for additive, especially as additive is becoming more and more production ready. So shortly after getting into the 3D printing business, it became clear that not just prototype, but end-use parts were possible with these machines. But you needed to design for them just like you would design for a stamping press or an injection mold. Maybe. There we go. But then everyone says to that, but I thought 3D printing gave you unlimited design freedom. Well, it does. You can literally design almost anything and 3D print it. But just like anything, if you actually design for the 3D printing process, if that's how you know you're going to produce your product, you can do things like make isotropically strong parts, which are parts that are not just strong in X and Y, but also in the Z direction, and that can be accomplished through making some upfront engineering decisions. You can cut post-processing time. So with a lot of technologies like SLA or FDM, it comes out, you've got all that support material on there, and you might have to sand all those surfaces if it's a surface that your customer is going to see. And I can tell you, hands down, the printing isn't what's expensive, it's the post-processing, because it's a person, it's a craftsman sitting there sanding on your parts. So you can do things with orientation and orienting your parts to reduce that support and save yourself money in the post-processing. You can gain additional and unique features in your part design, so things like integrated springs, printing an assembly that would typically be machined as multiple pieces, printing that as a single piece. You can do trapped components. I'll show you an example of that here in a little bit. Non-machinable, non-injection moldable, and non-stampable features. So kind of the holy grail of you can kind of draw these really wild features and be able to print them, and you couldn't really make them any other way. And then you can lower your costs. So in the case of low volume production, 10 to 5,000 units, 3D printing, specifically things like SLS or HP MultiJet fusion, those technologies can be very competitive with injection molding at lower levels. But again, you got to design your part for those processes to really capture that value. So the following are examples of parts either designed specifically for the 3D printing process or that were redesigned for it by our engineering department. So let's get into it. So first thing I'm going to do is I'm just going to quickly go through each technology in case people in the room aren't familiar with it. So this is just a quick synopsis of SLA. So SLA is a resin-based process. You essentially have a platform that goes down into a vat of this resin, and the resin is UV reactive. So when UV laser hits it, it hardens in the area where that laser touches. Now you still have to build support, just like a MakerBot or anything like that. You have to support the part. And so what it does is layer by layer, it's building and hardening those layers. This is traditionally used for prototyping. That's where, you know, SLA was one of the first, I believe the first commercialized 3D printing technology in like 88 or 90, somewhere in there. So it's a legacy technology, but, you know, still used a lot in prototyping, and we have found some very specific applications where it makes sense for a more mass production type of environment or use. So this is an example. It's called a blow vac block, and this is one of the very specific applications where we found production on SLA beat pretty much everything else. So the challenge, design a block that could route both high pressure air for blow off and a strong vacuum for removal of dust off of a part. So essentially, a part continuously moves across here with dry powder coat on it that hasn't been baked on yet. We want to break that powder coat loose off the bottom, vacuum it away, but leave it on the top surface that's traversing over this. So we call it a blow vac block. We use CFD to kind of figure out where all of our air nozzles need to be and where our vacuum chambers need to be and how big those vacuum mouths needed to be. And just because of how complex the geometry of this was after all that analysis, it didn't really work to manufacture it any other way unless you're going to break it up into a whole bunch of pieces and machine each one of those. So that's why SLA is fairly expensive, but it was still cheaper than doing it through traditional manufacturing. So kind of diving into this from a design for additive perspective. So the 3D printing allowed for the HPA holes to be arrayed at very specific angles and locations. That was called out for by CFD. So I wonder, can you see? You can't really see my mouse, but you have this array of holes up here. So each one of those, that angle was set very specifically to get the results that we wanted. And so one of the things we have is a central tunnel that goes down the center of this part, and you can see in the cutaway, it's like an arch. And the reason we do an arch can be self-supporting when we build it. So, you know, we're building this as a single piece. If we built a bunch of support inside of this, we'd never be able to get it back out, and it would plug up our works. So by using arches and round holes and draft angles over 45 degrees, we didn't end up with any support material trapped inside the block. So when we were done building, all that extra resin drains out of the block, and you're left with your part. And so you don't have to print it in multiple sections. One of the tools that I use a lot is the SOLIDWORKS draft analysis tool. Most of the time it's used in injection molding to check your draft angles and things like that. It works in situations like this too. If you know you want to make sure there's no angles that are going to fall below that 45-degree limit, you can plug it into your draft analysis and actually color code and check. And on very complicated parts, that's a really handy thing. So let's see here. Yeah, and then another trick is to keep costs down on this. Remember what I said, manual sanding is very expensive. So by building in this orientation, all of our nesting or all of our support material was on this nice flat bottom. So you could literally rip it off the build platform, set it onto a piece of sandpaper, scrub it like for a minute. The bottom is totally flat. So you have just greatly reduced your amount of manual labor, which again is very expensive, by just making sure you had a nice uninterrupted flat bottom on this part. So, you know, when you're doing SLA or you're doing MJ or you're doing FDM, anything that requires support, always think about someone's going to have to take this support off, and that's going to cost me money. So anything you can do to make the part self-supporting will save you money. Okay. So now we're on to our next technology, which is MJF. So MJF is like SLS, but pretty different. It's an area process instead of a point process. So essentially you lay down a layer of powder, and so this is like a finished layer below, and you can see the black is a solid part, the particles are the loose powder. They're laying down a fresh layer of powder, then they're going to, carriage is going to come across, it's going to spray down a fusing agent, and it's going to spray down a detailing agent. Fusing agent causes all of those particles inside of it when they get hit by intense IR light, causes all those nylon particles to sinter to each other and to the layer below it. The detailing agent prevents all the loose powder around the outside from sintering. So all that powder stays unsintered, and your part is what actually gets sintered together. Cool thing about this is, like I said, it's an area process. So whether you have one part or 100 parts in that layer, it's like, I think it's 19 seconds per layer or something like that. So it's very, very good for production. That's where we get into like low volume production, is on this type of a machine. So jump into. There was a photo of. Picture was brown. Did it not? Did the video not play? Oh, okay. So I have a picture of one of the machines right here. That's what that one to the lower left-hand corner, HP MultiJet 4200. That's what the printer looks like. All right. So this is an example of one of the products that we redesigned to be produced on MJF. So the challenge: take an existing safety cover for a high-speed ratchet assembly tool and redesign it from a machined Delrin plastic part to a 3D printed PA12 nylon part. That's the material that the MJF machine prints in. Decision to move from machining to 3DP was driven by two factors: lead time and cost. The annual usage of this part is only 300 to 500 units, and the diameter changes with every run. The customer could not justify injection mold and was machining them. Lead times and machining costs had steadily increased for CNC machines used to make these parts over the years. And so eventually the customer got to the point where they were getting 4 to 6 week lead times and they just couldn't stomach it anymore. And so we came in and quoted it and actually beat what they were paying for machining. But there were some challenges that had to be overcome. So one of them was, originally this was machined as a solid round part, and there was a detent inside there that would snap onto this ratchet. Well, when we initially printed it, we went to snap it together, and the nylon just shattered because it's not quite, doesn't have quite the flexibility that Delrin does. So we all kind of sat there and looked at it, and someone said, well, what if we made it like pedals? What if we kind of built a living hinge type concept? And it was very simple. We literally cut 4 slots, broke it up into quarters, and that thing snapped together beautifully. And so, that's one of the things that, when you're going from like a machined part to a 3D printed part, like sometimes you can't just directly go from one to the other. Sometimes you have to get a little creative with your geometry. And that is kind of what I'm trying to show here is, just, get creative and figure out a way to make it work. Another requirement that came down with this, now this was something that was new for 3D printing because the customer said, hey, if we're 3D printing these, can you put the size socket on the outside of the part for us? And we're like, yeah, but the problem was there was like 35 different socket sizes that we were doing, and we were just we made up a start part essentially where we were just cranking through these and creating all the different sizes. So another trick we do when there's labeling, but there's like high mix type labeling where you're constantly going to be putting a different label on the part. How many people in here use Property Tab Manager? There should be a lot more hands. It is a really, really great way to take your part properties and bring them right out to the side of SolidWorks. But essentially you can use Property Tab Manager or you can use your summary information, but essentially we have a field called Note, or Notes in this case. And very simply, when you set up your sketch and you put your text call out on that sketch, you can actually tell it, query that notes field for what I want this to actually say. So instead of having to go in, edit a sketch, double click on the thing, write in the text box, green check, back out, rebuild, you literally just pop open your Property Tab Manager or grab your summary information, hit it, type it in, and hit rebuild, and it's done. So for high mix labeling, that's kind of a little hack that we've come up with to make it less of an arduous process, especially if we have a start part that we're working off of. Okay, end of arm gripper fingers. So DeWise Engineering, probably 50% of our business is automated equipment. We design a lot of automated equipment for a big variety of industries. And so one of the reasons we got MJF was just because we had so many people coming to us and saying, hey, we want to do this really exotic end of arm tool, or what can we do to save some weight on gripper fingers? And so, you know, we got a hold of one of these machines and we started doing custom gripper fingers. So one of the challenges, in this case, we're talking about the gripper finger you see there in the middle. The challenge, reach into a very tight space in an injection mold and place a part for overmold. Due to the number of grippers required, the end of arm tool, they need to be very lightweight. The grippers also need to house vacuum cups. There would not be enough room to route the vacuum lines along the outside of the gripper fingers. They need to be routed through it. So, let's flip over to the next slide here. So this is a SOLIDWORKS model, and I'm kind of showing you the same assembly just cut away, and so you can see the suction cups and the internal lines. So one of the things that's really cool with 3D printing is you can print crazy airlines, you can print, you know, liquid passages, you can print vacuum lines, you can do all of that. And there's no, you know, you think about if you're doing it in machining, you're going to be cross-drilling everything. So, you know, that's the way you're going to have to do that, or you're going to have to make it bolt together. Whereas here, you can literally say, here's where I'm going to start, and here's where I'm going to end, and I'm going to use a 3D sketch and just wind my way through there, and then literally sweep a hole all the way through. So that allowed us to place those suction cups where we needed them, but get the vacuum fitting, or get the air fittings out of the way so that we can clear when we're going into the mold. Another thing is, you know, this is a fairly complex geometry. Now, we just kind of threw this one in particular together for this demonstration, but, you know, if you had to sit down and figure out how you're going to machine this, putting aside the airline that's going through it, but just machining the outside, you know, you'd have to, you know, do a couple setups in a Haas, or you'd have to bump up to, you know, a 3 or a 4 or 5 axis machine. You know, it's all very expensive and time consuming, you know, especially where we're at, which is Western Michigan. You know, trying to find 5-axis machines sitting around with nothing to do is almost impossible. So when lead times are an issue, that can be a real limiting factor. So, you know, we're able to print 2 of these gripper fingers, and out the door, it's 3-day turnaround and like $350 for the set. You know, and so it's very, very cost effective for our customers to go this route and get that design freedom. And then lastly, like I said, there was a bunch of these gripper fingers that were going to be on the end of arm tool. So this part in aluminum would have been 0.4 pounds, and in nylon, the part is like 0.2 pounds. So, you know, it's quite a weight savings if you're trying to cut weight out of an end of arm tool. All right. So this is kind of a fun one. I have a buddy of mine who's a photographer, and when he came over and saw the machine for the first time, he said, "Hey, you know, could you make custom, you know, camera lens covers with something like this?" And I'm like, "I don't know. We can make anything." And he's like, "Well, could you make them cost effectively?" And that's kind of where the challenge got thrown down. So the challenge was allow for mass customization / production of camera lens covers while still keeping the cost to the consumer at under $35. To cut down on manual assembly and hardware costs, the cover needed to be printed as an assembly with built-in 3D printed springs. So this is kind of one of the things you can do, again, with 3D printing. That's, you know, people have been injection molding springs forever, you know, making a part that's got a built-in spring. That's nothing new. But, you know, the thing here is we print it not only with the spring, but we print it as assembled. So as you see it on the screen right here, it actually comes out of the machine like that. But if you're going to print assemblies, there's some real tricks that you have to keep in mind. The biggest one is if you get the parts too close together, they will sinter together. So with MJF technology, we typically will leave, depending on orientation, an 8 thou to 10 thou gap between features or between parts in the assembly. So, you know, you can't necessarily print, you know, 2/10 of clearance or anything like that, but if you have a product that can have a little bit of slop or can be a little bit open on tolerances, you can print it assembled. Another thing you got to think about is in the case of like an SLS or an MJF machine, all that powder, you know, it builds layer by layer. All that powder stays in there because the powder is the support material, okay? So if you print something, you got to make sure that you can get the powder back out of it. So we always try to think about, you know, if we're standing there with a bead blaster and then an air gun and we're depowdering these parts, what's the path that this powder is going to travel to get out of the part? So it's a little bit hard to see, but this bottom view right here, this gap that you see all the way around here, that is not only to keep the parts from fusing together, but that is to allow powder to, you know, clear out of the part as we're bead blasting it. And then springs. So, you know, springs, like I said, they've been something that's been done in injection molding for a long time. The best thing we found is, you know, we're using PA12, so you can use, you know, a lot of knowledge you have for spring design and plastics from like a nylon type material. But generally speaking, there's always going to be some variation, some differences. So we tend to take and print, you know, 2 to 3 variations of a spring design and test them all, figure out which one we like the best, and then just start iterating on that design. And, you know, usually within, you know, probably 5 parts, we've got the spring dialed in, and we're getting a nice, you know, a nice spring return force, and it's holding up to long-term use. So yeah, so the best rule of thumb for spring design is plan on doing a bunch of them, and eventually you'll dial the spring in. We haven't really found any like hard and fast rule for this works every time. It seems like it's very geometry dependent. All right. Oh, and lastly, so remember, the challenge here was to also cut cost. We're trying to get to that $35 mark. So excess material, you know, you want to try and cut excess material out of your part anywhere you can. Now, if you think about like, you know, CNC machining, for example, every bit of material you're cutting is cost, right? So, you know, sometimes you're like, well, if weight isn't a big issue and I can leave this material in place, you know, I'm not going to chew it all out. You know, you look at like what aerospace guys do for hydraulic, you know, manifolds, and they got these crazy organic 5-axis shapes, but they need to get every pound of material out as possible. You look at a hydraulic manifold on a bulldozer, it's just a block with a bunch of holes drilled in it, okay? So for us though, it's the opposite of that. So the printer doesn't care how complex your geometry is. Like I said, it's going to run at 19 seconds a layer no matter how complex your geometry is. So for us, you want to try and get as much material out of your part as you can because you're paying for that material. Now granted, it's pretty cost effective. The material isn't the biggest cost driver with this technology, but every little bit helps. So, you know, anywhere that you can get material out, you're going to want to do it. And, you know, generally like plastic injection mold rules where you want to have consistent wall thicknesses and things like that, you can definitely get away with having heavy and thin wall sections all over the place. But if you can keep consistent wall thicknesses, again, it saves you material and it just produces a little bit better part. So that's kind of something to keep in mind. So end result was when we printed, I think we could get 200 of these in the machine at a time, and we could get them down to that price point when it was all said and done. So that was kind of the end result of that one. All right, so our last technology that we're going to cover here is FDM. So this is probably the most common 3D printing. When people think 3D printing, they generally think FDM. Now this is showing like a higher end machine like a Fortis or Dimension, but a MakerBot or a Markforged, those all kind of fall under this umbrella for the most part. So essentially I like to call it CNC controlled hot glue gun, okay? You got a barrel that's heated, you're feeding extruded wire, or not wire, but plastic wire into it, and layer by layer it's extruding that plastic and it forms your part. Now remember, the first technology we looked at was SLA. You had to have support material that had to be taken off. SLS and MJF, which we just finished talking about, are powders, so there's no support material that has to be removed. But with FDM, we're back to having support material again. So when you're thinking FDM, think someone sitting at a bench removing this material and post-processing these parts. So that's some of the stuff we're going to talk about. All right. So, example, tape applicator. So, the challenge was design and 3D print a series of ABS plastic hand tools that can be used to guide the application of tape onto windows during assembly. So, one of our big customers is a tape manufacturer. And if you have double hung windows in your house, they are held together by tape. Like the whole window is held together by tape. And so they're all assembled manually with our customer. And so one of the things they give their assembly people is they give them these tape blocks, these guide blocks. And essentially it will fit onto the profile of the edge of the window where they're trying to lay down that tape. So they'll start the tape, they'll pull out a length of it, they'll put this guide on there, and they'll pull towards themselves, and it does two things. It guides the application of the tape, and it wets the tape out at the same time, because they would guide it on by eye, and if they got it right the first time, they didn't have to pull it off and try it again. Then they would take a roller, and they would have to sit there and roll all the bubbles out of the tape. So this applicator kind of does both those steps in one go. The issue our customer was having, though, again, it's a high mix. There's a lot of different windows that they're making, and they're always adding new ones. And it was just very, very costly for them to have to CNC machine these out of, I think they were using Teflon or Delrin or something, one of those engineering grade plastics. And it was just very expensive for them to constantly be making these, and then they'd use them for a month, and then the window would change, and they'd throw them all away, and they were just churning through these. So they came to us and they said, what's a low-cost solution here? What can we do to save ourselves some costs and make something? So we came up with V1, which is the one over here, and it is literally, these were all run on a Axiom, which is from Airwolf, and it's like a MakerBot. It's kind of in that class of equipment. And we designed it so we could cram, I think, 10 of them on a build platform, and they would run for, I think it was a 15-hour build, and every 15 hours we were cranking out 10 of these. And eventually the volumes got so high that we had to jump to a Fortis machine because we just couldn't keep up with the Axiom. And so let's see. Yeah, we'll skip to the next slide here. So that V1 that I showed you, that's what we started with. Well, then, as customers tend to do, you give a mouse a cookie and he's going to come back and say, yeah, but now can we put a wet out roller in it? So that is what this is. This is version 2.0. And so I'm going to trip and fall off this frickin' stage, and everyone's going to laugh. All right. So what we did is we made it a two-part design this time, and we put actually a Delrin roller into it because the last ones worked off of friction for wetting out the tape. And the customer wanted to get back to actually rolling the tape to get all those air bubbles out. So this is where you start to come into like a hybrid of like additive and like some traditionally manufactured components coming together into an assembly. And then we literally just have shoulder bolts that hold the whole thing together and act as an axle for that roller to run on. So let's see, some design tips for FDM. So remember on the MJF side of things, it was like that 8 to 10 thou clearance around your features that need to get powder out. Well, with FDM, we found that you have to bump that up to more like 0.025. That's where you're going to need to be for clearance because it's just a less precise technology, and so there's a little more variable in there. So we give it a little more open tolerance. Let's see. And then another trick, so you want nice round holes because you've got round parts sitting in these pockets and you want them running in nice true round holes. Well, originally we were building these standing up and we would have to go in and print everything undersized with like a triple heavy wall and then ream it to get the holes round because it would print like egg shaped. So what we realized is if we split this in half, we could lay it open like pieces of bread for a sandwich. Now our holes that we have those critical round diameters on are facing straight up in the Z. So they print in a really nice circular path because the machine, there's not support in there. The heat doesn't cause them to sag as the part is building. So if you have supercritical round hole features, and this kind of goes for every 3D printing technology, but specifically FDM, point those holes straight up if you can. And that will give you the best tolerance and size you can get on an FDM hole. Another trick, so you know, this, remember, there was support. There was support that had to be generated under these parts. We figured out that if we took and had nice flat bottoms, we could actually print these with zero support. We could print them stuck directly to our build platform without any support underneath of them. And now, when they come off the build platform, there's no support that has to be ripped off, and we don't have to do any sanding on those faces because they're as smooth as the glass bed of the machine that we printed them on. So the only thing we had to do at that point was there was almost a burr around the outside of those flat faces. Just run around it with a deburr tool and peel that burr off. And now we just, again, cut more time of a person sitting there manually doing something. And again, that's what drives cost. So, you know, anytime your FDM part, you know, can stick directly to the bed, you're going to get better surface finish on that face, and you're going to get away from that much more post-processing. Let's see here. Oh, and then, yeah, just another last quick thing. The feed ramps. So you can see the angled ramps that go up to that blue roller. Again, when we were building that straight up and down, we were getting a lot of stair stepping in those ramps, which was causing our customer to have issues. By laying it down, it's a continuous straight motion throughout the entire angle of that ramp. So you get nice, true angular ramps instead of like a stair step type ramp from all those layers building up. So just kind of think about stuff like that. And believe me, this didn't happen the first time. There's like 10 of these that came before this where we were figuring all this stuff out. So like, I can't stress enough how iteration is super important for additive type production. Like, you're not going to get it out of the gate, but the nice thing is there's no tooling that you have to recut. There's no arguing with, you know, shops about lead time for getting it back onto the CNC. Just print another one, you know. Okay, so that kind of takes me through a bunch of the examples. Oh, go ahead. Absolutely. But the issue, and we did that on one of the iterations, but the issue was I'm the guy who lives the closest to the office, so that when at 3 o'clock in the morning someone had to be there to place the nuts, it always happened to be me. So after a little while I said, you know what, we'll just put them in afterwards, but you can absolutely do that. You know, literally, you know, these desktop printers, they're wide open. They're mostly, you know, open source, so you can get in and do really cool things with the code and stuff like that to add pauses and things like that. I know it can be done on the big Fortises as well. I don't know as much about how you go about getting pauses into those programs, but I know I've seen people do it there too. So biggest thing is, if you're under... Yes, I'm going to get to I got a slide coming up just for you in a minute. So yes, the issue we had on this one though is we had to really torque those together, and we were pulling the threads out. So Yep. Yep. Yeah, so we use the Kapton tape. It's the same basic idea. It's just a release agent. Yep, yep, the wolf bite, I think. I think it was pretty much we ran out, and then we had a roll of Kapton tape, and then now we have Kapton tape on it. So, yeah. Oh, the Gecko Tech. Yeah. I didn't have very much luck. I've seen people have really good luck with them, but I haven't. So no. All right. Then any other questions? Oh, the cone, the locating cones. That was definitely probably 2 or 3 spins, because we wanted to get them really, really close. But exactly, if they're just a little too close, then all of a sudden you have a gap in the middle. And that is another thing. By laying them down, you get a much shorter build, and the shorter the build, the more accurately you can control features coming together like that. So, try to, the smaller the better to a point, and then there you can get too small. But yeah, that's one of the things we ran into. Okay. So now I've kind of hammered through a whole bunch of design for additive stuff. Now I'm going to drop into some SolidWorks tools that I specifically use for additive and that are really, really useful. So we already talked about the labeling trick. That was one of the things we used quite a bit. So I think, there we go. So 3D texture. How many people were in the general R&D session this morning? A couple of you. So all of you guys saw this morning, they were up there and they were talking about the ability to take a grayscale texture, put it on a part. Well, for any of you that weren't there this morning or aren't aware of this, in SolidWorks 2019, they added an enhancement, or a feature, if you will, and you can take and you can download, and actually these are textures on the left right here that are actually built into SolidWorks, and they're grayscale textures. And you can drop them onto a part. We've done it on a lot of flat surfaces. We've also started experimenting with doing it on like organic surfaces. There are some real limitations with organic surfaces, especially just grind time. You hit green check, like go to lunch. Like if it's something big, you will come back from lunch. It still won't be done, and then you start it again when you leave at the end of the day, and it might be done by the time you're back. I think this tool needs a bit more time in the oven, but I love where SolidWorks is going with this, because what you can do, you take this texture, you apply it to your block, and then SolidWorks will actually look at the black and the gray and those transition areas between, and it'll actually take and make that texture 3D on the block or on the face of the part. So it's insanely hard to see on this guy, but these are all in the same orientation. So you can't, this just is a mess of STL data, but you can sort of see there's a hatch pattern in here. That hatch pattern corresponds with this right here. It actually creates raised features on the part. And then my guys took the part that we had printed on the MJF machine. It comes out gray, and they dyed it black, and it's almost impossible to see on the screen here. But I promise you that black blob on the right-hand side of the screen does have this texture in it. It worked out really, really well. And so what we're starting to do is experiment with some of our product development customers around letting them say, hey, we want to put this wild texture onto this surface in this area. And it's not moldable, and it would really suck to machine, but it doesn't cost you anything to 3D print it. If you came to me and said, Paul, quote me that block that's flat surfaces and quote me that block with texture on every side, there'd be no difference in the price. It's literally the same. It's such a minute amount of material, but you get a completely different result by being able to put this texture on. So if you go in the SolidWorks and you go up to the command bar and you can search for commands, if you type in 3D texture, this tool will pop up. There's some tutorial videos on YouTube that'll kind of get you going with how to find a texture. And like I said, SolidWorks has some textures built in, but if you want to get your own texture off the internet or make your own texture, this is something that you can use, and then you put it on your part and you can get some really cool results out of it. So definitely encourage you guys, if you haven't played with this, give it a look. It's pretty cool stuff. All right, let's see. Threads. This is for you right there. All right. So like I said, on the engineering side of my business, do a lot of machine design. First thing we do when we download anything off McMaster is they have all those threads on every fastener. Get rid of all those threads, because all it does is add a ton of computation time to your assembly. So if you've got a machine with 1,000 fasteners in it, it'll crush you. It'll kill you. Large assembly mode won't even save you. So we get rid of all those threads. And I've always thought, threads in design, there's such few cases where you'd actually need it. Until I got into 3D printing hardcore, and I started thinking to myself, what about printing threads? What about printing a part with the threads in? And so we started doing some R&D around this just to kind of see what we could come up with. And what we found is if you take Hole Wizard and you pop a hole in your part, and we'll just use a, you know, I think this is a half 13 is the example we're looking at. So you pop in a half 13, it gives you your drill hole size. And then if you you grab the thread tool and you pick that top surface, that top circular edge, and you tell it you want a half 13, and there's a million other options you can play with for, you know, start position and offsets. You know, it's pretty straightforward. If you play around with it, the command isn't that hard to use. But you put that in there, and all of a sudden you have a hole that's threaded, and so you can bring that over. And we've experimented with it on our SLA machine, which is the first one we saw, and we've experimented with it on our MJF machine, which is the second one that we looked at. And we found the MJF machine did the best job, especially on smaller threads. And essentially, you print your hole with your thread in it, and then that eye bolt literally downloaded off McMaster. It's already got the threads on it. We printed them, and they screw right together. I mean, we're not putting offsets on anything. Like, it literally just went together based off of the old machinist handbook, you know, having the correct clearances on both sides. And so we're like, well, that's really cool, but how robust are these threads? You know, what's the pull-out force? Because we've already drilled and tapped this material before, you know, specifically in FDM, and we've had thread pull-out issues, especially with steel fasteners. So we did 3 tests. We did a 1/4-20 eye bolt and block. We did a 3/8-16 eye bolt and block, and then we did this 1/2-inch eye bolt and block, and we put them into a pull tester. And all of them failed, but the threads didn't come out. It actually failed at the cross section where the first thread is on that eye bolt, so where the diameter gets the smallest. 1/4-20 failed at 250 pounds, 3/8 failed at 350 pounds, and 1/2-inch failed at 900 pounds. So we were shocked. We were like blown away. We expected the threads to come flying out of the hole and the whole thing to come apart. So that would be, if you're going to do printed threads, this is the workflow to use right here. Saves you a lot of time and a lot of screwing around. Standard 2 times. Yep. We went with just a standard 2 times thread engagement. And like I said, you know, that's a good question. I wonder, you know, how low you could go before the thread started to fail. I don't have an answer for that, but someone in here should try it. All right. This is nylon PA12. Yeah. So. Nope. Finger tight. Nope. Took it down to finger tight. Okay. So we're running. Let's see. It's 3:30. This ends at 3:45, I think. And I did throw a bonus slide in here for you guys. So before I go into that, any questions? Okay. So I get into a lot of weird projects. Okay. When you couple engineering and additive, a lot of interesting people come knocking. For example, we had a company or a lab come to us and say, "Hey, we are a medical firm, and we need a MRI fixture to hold dogs in an MRI machine while they're sedated." And I'm like, "Okay, we could do that." I'm like, "Why additive?" Like an idiot. And they said, "Well, we can't have any metal in the MRI machine, so it can't be machined, it can't be cast, it has to be plastic." And I'm like, "Okay, that's a pretty good reason." So the challenge here, a medical testing lab needed an all-plastic fixture. Due to the fact that the fixture was going into a magnetically active environment, there could not be any metal. Also, the fixture needed to be extremely adjustable to accommodate dogs of many shapes and sizes. And I promise you, no dogs were hurt this is to help dogs. This is not to hurt dogs. It looks very medieval, but it helps the dogs, I promise. Okay? So this is what we came up with for them, and we did a mixture of all of our different printing technologies kind of coming together on this. The bulk of it was FDM. but one of the things we found was we needed to fasten this whole thing together somehow, and we needed threads and everything so that there was a lot of adjustability. And we found that on McMaster, they sell plastic threaded bolts and stuff like that. So we actually bought those, and then we would drill and tap all of the holes in our FDM parts. And the thing we realized was, you know, if you're going to have a plastic thread and you're going to have a plastic fastener, the plastic thread, you always worry a lot of use. It's going to wear out running against a metal fastener. But if you're using a plastic fastener, they actually kind of wear at the same rate. So you get a lot more life using plastic fasteners. So if, for example, you did have an application where you wanted to have printed threads and you were going to be adjusting it a lot, consider using, if the loads will permit it, consider using a plastic fastener instead of a metal fastener, and you'll get a lot more life out of those printed threads. That's one of the things we found here. And then a couple other points. Again, we had to load some of the areas of this with mineral spirits for alignment. Mineral spirits will glow in an MRI machine, so they would use those targets to align their MRI machine and get their scans where they needed them. And again, we already kind of covered this, but you know, they needed really, really round true features and really square true features. So orient those vertically in the Z direction, and you get really good, clean results that way. And we found a really good result doing it that way. Okay, and that's pretty much it. So this went a little faster than I anticipated, so we've got some extra time. So if, no, unfortunately, no pictures allowed there. But I got to see it, and it's just an unconscious dog, and they kind of put its mouth onto the let's see, yeah, an unconscious dog is weird. It's weird to see. Yeah, they take and essentially rest the top teeth up here, and the jaw just kind of hangs down here, kind of slack-jawed. And then they use these to position other parts of the head. And then these are actually loaded with mineral spirits. So that's what they use to align to do scans on the dog's head. And I'll tell you what, in researching this presentation, this is a complete aside, if you want to see something really crazy, type in racehorse MRI. There's a company that builds MRI machines specifically to X-ray, or not X-ray, but image the knees and ankles of these super expensive racehorses. Like, it's a whole cottage industry. That's all they do. They just are for racehorses. So I thought this was weird until I saw a horse laying in an MRI machine. Any other questions? All right. Well, everyone, thank you so much. I really appreciate it. Oh, by the way, for those who stuck around, I didn't expect a crowd this big. I have a bunch of 3D printed parts for you all to take if you want them. I don't think I'm going to have enough, but if I don't have one for you, give me your card, and I'll get you some in the mail. So if you want to come up here, I'll hand out some parts. Let's see what we got here. So some of these I got to hold on to, but a bunch of them we can give away. Let's see. That one I got to hold on to, and that one I got to hold on to, and these I got to hold